All right, hi. We're just gonna dive right in, because there's a lot to go over. But hi, welcome back to Math 234. I'm your host, Steve DeGroot. Today we're reviewing for exam number 3, where all of our topics are just gonna be chapter 15. Usually this exam includes the last section that we did, curl and divergence, section 16.5 out of chapter 16, of course, since that's it's heading there. But it's not going to get featured this year. This year, of course, being fall semester of 2025, just in case you are watching this video in a semester that isn't that, look on D2L for the correct information. Same thing goes for those of us here in the classroom, though. D2L should have all of the up-to-date information on what the exam covers. And again, I think we were pretty explicit that it does not cover curl or divergence, which means you won't see any review of curl or divergence in this review. Use the same word twice on accident. It's not my fault. I was thinking of something else. We're recording, aren't we? Yeah, we are. Okay, good. Great to check on that now. Hey, why are we being like that? All right. Again, we're diving right in. So let's start reviewing stuff. And I'm going to go in kind of reverse order this time. Do the stuff that we just did first, and then work our way back to the beginning. Starting with change of variables. There was a lot out of that section. If you've looked at the web work, I think you know exactly what I mean. We are going to focus pretty much exclusively on the Jacobian matrix determinant calculation. Right, so the Jacobian is the thing that's responsible for the R that we have to multiply into dA or dV if we're in polar or cylindrical coordinates. The Jacobian is also responsible for the rho squared sine phi that we need in every triple integral we do in cylindrical coordinates, that extra bit that we multiply in order to scale our region to match the integral that we want to do. So again, we're focusing pretty much exclusively on the Jacobian matrix itself, and significantly less the transformation of spaces and finding new equations and all that kind of stuff. As you probably saw, that stuff can be tedious, so just focus on what is it? Just focus on the Jacobian transformations. So what I mean by that is be able to come up with one of these matrices, which should look like the thing that's at the top of the screen. The x partials go across the top row, the y partials go across the bottom row, and then we do partial derivatives with respect to our two new parameters. Usually we just go in alphabetical order, so we'll put u down the first column and v down the second column. In particular, if you're looking at web work, I think you have to get them all in the correct order before it marks it correct. So if I just go through and look at those, let's see, x partial u is v, x partial v is u, since that's just the product uv. Y's partial derivatives, y partial u is going to be 1 over u squared. And the derivative of y with respect to v is going to be negative u over v squared. And I can see that something's already gone wrong. That only should have been a 1 over v, not a 1 over u squared. I don't even know where I got that u squared from. Probably just talking too fast. So that would be the 4 entries that go into our Jacobian matrix. The thing we're particularly interested in is finding the determinant of that matrix. On the exam, we might have just called the determinant J, whereas here in the web work problem, we're calling the matrix J. But the wording of the exam problems should be clear as to what we're looking for. So on the exam question, I know we're going to be asking for the actual determinant calculations. I'm just adding on to this web work problem to get that. So the determinant of this thing should be v times negative u over v squared minus u times 1 over v. All right, we just multiply the diagonals together and then take their difference. So pretty similar to a cross product. The other thing that's important about these determinants, when we're looking at determinants of Jacobians, oftentimes just called Jacobians, They need to be absolute values. Well, come on, whatever, close enough. So I need an absolute value of this thing. So I end up getting, what does that look like? Negative 2u over v would be my Jacobian there. And I would probably need some sort of information about u and v to know what to do with this absolute value. But I suppose I could at least evaluate out that negative that's in there, or absolute value that negative in there out. But I would also need to know, like, are u and v both positive? Are they both negative? Is one of them positive? Is one of them negative? We would need to know more stuff to fully evaluate that determinant. So instead, I'll just leave it as its absolute value. So one of the things that's sort of nice about calculating these determinants with the absolute value involved, if you mix up the order of your partial derivatives, say you put the v partials in the first column and the u partials in the second column, so just backwards from the way that I did it. While our Jacobian matrices won't match exactly, our determinants will. Because if you just swap the columns, all that's going to change is the sign of your answer. You'll still get the same 2u over v product, but you would get a positive sign, whereas I got a negative sign, which is just what happens if you transpose those columns. And because we're taking the absolute value of the Jacobian determinant in the end, the order of the columns doesn't matter, which is kind of nice. So even if you mess up exactly the order of what that Jacobian looks like, as long as you're consistent within your rows and your columns, you'll still end up in the same answer. So even if you put like x and y down the columns and the u and v partials across the rows, your determinant calculation will still come out right in the end. Again, because we're taking that absolute value. So focus more on just, getting the stuff into the matrix and taking a determinant, and less about knowing its exact order. Though its exact order is helpful. Don't want to super diminish the importance of that there. But anyway, let's get on to the next one. Might as well do all three of these. We need S and T partials this time. Again, we'll order them alphabetically. So S comes before T, which means my first derivative is going to be 2 e to the s minus t. Or 2e to the 2s minus t. There we go. Right, derivative of an exponential function is that. So that's x partial s. X partial t is going to be negative 1 e to the 2s minus t. 2s minus t. Across the bottom row, we want the y partials. So y partial s looks like 1 e to the s plus 2t. And y partial t, 2e to the s plus 2t. And we might as well go get our determinant here as well. And what does it look like? This is going to be 2e to the 2s minus t times 2e to the s plus 2t. If I go across my first diagonal column, my second, I'll have a minus negative e to the 2s minus t times e to the s plus 2t. And then I think this can simplify. Don't forget the rest of your absolute value. To 5, since that's going to be my overall coefficient. 2 times 2 is 4, plus 1 is 5. Notice that the things being multiplied together are the same. And if I'm multiplying two exponentials, I can add their exponents to get 3s plus t. And you might have noticed I have dropped my absolute value sign. So what gives? Last time I needed to know stuff about u and v, but why not this time? Well, I know the range of an exponential function in particular. Exponential functions, if they don't have any like vertical transformations on them, their range is always positive, 0 to infinity. Open at both ends. It doesn't matter what the exponent is. My exponential function is always going to be positive. So the domain of S and T don't particularly matter here because exponential functions are positive already. So I can evaluate that absolute value for this determinant, whereas I wasn't able to fully evaluate it in the previous problem. So fun stuff there. For the last one, let's do a 3x3 Jacobian matrix. So again, we'll order these things alphabetically. So U, V, and W in that order, since that's alphabetical order. And X, Y, and Z are as listed there. Let's get some derivatives. So X partial U is first, and that's just 0. We'll zoom in a little bit here. Then I want X partial V, which is 2V. And then I want X partial W, which is 1. Next on the list, Y with its partials. Y partial U looks like it's 1. Y partial V is 0. And Y partial W looks like 2W. And lastly, Z's partials. Partial U is 2U. Partial V is 1. Partial W is 0. And if I want to try the Jacobian of this thing, which we might as well do, I just need the cross product of this mess, effectively. That Jacobian comes out to 0 times the 2x2 matrix that's in the lower right quadrant, right? So I'm dividing like here and here. Let me just use a color to divide that out. Dividing there and there. So I've got the 0 in the upper left times the 2x2 matrix that's left over, which is going to be 0 minus 2W. Up next, I've got 2V times the resulting matrix that comes after that, which if I just kind of fill in some extra elements over here, 1 and 2U, I'll just bring my first column over to the right edge so that I have a 2x2 space to calculate my determinant right there. That thing looks like 2W times 2U, which will be 4UW, minus 0 times 1 is 0. And then for the last one, plus 1 times the matrix on the left, or that 2x2 determinant on the left, which is 1 times 1 minus 0 times 2u, would be just 0. Don't forget your absolute value signs. And then we can calculate that bit. It looks like it is 8u v w plus 1. And again, since I don't know any information about UV or W or what their domains look like, I'm going to leave the absolute value in. I'm not able to resolve it unless I know something about the variables this time. Because that is not a function that's always positive, unfortunately. Cool. So that's my 3x3 matrix determinant, or Jacobian determinant, I suppose. Yeah. All right, let's look at the next one, which I think we're moving on, yep, to spherical integration. So WebWork wants a lot of individual steps. We're just going to evaluate the derivative as it stands. So we're looking for the volume of the sphere, given right there. Looks like it's centered at the origin, has a radius of 5, excuse me, and it lies in between the cones. z equals square root of 3 times square root of x squared plus y squared, and z equals 1 over the square root of 3 times square root of x squared plus y squared. So let's figure out what that looks like. I am going to jump ahead a bit here because these are common cones. We see them pretty often. Jump straight to our answer in case you already see that. This cone is phi equals pi over 6. The cone on the right is phi equals pi over 3. But we'll get to evaluating that in just a minute. So probably one of the things that I should do here is sketch what this looks like in the ZR plane. That's usually helpful. Put Z up there, R right there. R can represent the x-axis or the y-axis or anything in between because won't be any theta dependency on this shape. Because we're just going to go all the way around theta from 0 to 2 pi. But if I project into the ZR plane, the sphere looks like a circle. I'll call this thing, I'll label it down here, rho equals 5. Because again, that's representing the sphere. It just looks like a circle because of our projection. And I've got some cones. Cones will look like V's in this plane. If I look at their projection onto the other side, it might be like that, but usually we only focus on the half plane. So this is our cross section right there. That's the cross section of the volume that we're looking to evaluate. We're looking to find. With the cones being phi, come back here, phi equals pi over 6 is going to be the cone that is closer to the z-axis because this angle right here is going to be pi over 6. Oh, whoop, I made them purple, didn't I? Not blue. Blue is for later, I guess. The cone that's further away from the z-axis, that's phi equals pi over 3. Because this angle right here is pi over 3. Keep in mind a couple of other fancy things. Straight up is phi equals 0. This is still the z-axis. And straight to the right is phi equals pi over 2. All right, so just from the way that we define our angle phi in that 3D coordinate system. Quick note on finding equations of cones if we are in spherical coordinates. The equation z equals, I don't know, how about 1 over, just call it 1 over a times the square root of x squared plus y squared. These always look like cones. We can recall even all the way back to our quadratic surfaces lesson, 12.6, from very close to the beginning of the semester, when we looked at a bunch of quadratic equations in 3 space. We know that this thing is going to be a cone, z equals square root of x squared plus y squared. Since that looks like z squared equals x squared plus y squared, we're just only taking the top half of it. So it's a cone, and transforming that thing into spherical coordinates looks a little like the following. This is z equals 1 over a times r. I usually like to make that adjustment first. Square root of x squared plus y squared is r. Keep in mind that a is just some constant here. I just wanted to keep it general for a moment so that I could figure out what it looks like in the end. Z is rho cosine phi. R is rho sine phi. So this gives me the equation A equals rho sine phi over rho cosine phi, which is just tangent of phi. So I can simplify that. So I want to rewrite that equation right here. Tangent phi equals A, because that means phi is equal to the arctangent of absolute value A. So arctangents are defined in a really funny way, right? So are all of the inverse trig functions. So just be a little careful if you go to try to use one of those arctangent functions, because phi is either going to be the arctangent of the absolute value of A, or it is pi minus arctangent of the absolute value of A. Phi will be one of those two numbers. It just depends on whether we're in the top half of the coordinate space or the bottom half of the coordinate space. First equation, arctangent of absolute value of A, that's in the top half. So that's 0 to pi over 2. And the bottom equation, pi minus arctangent of the absolute value of A, that's in the bottom half of the coordinate space. So pi over 2 pi. So if A is a negative number, we'll have to go to the second equation to find the exact equation of our cone. Fortunately, we don't usually have to deal with the second half. Most of the time we look at positive values. I'm just going to gray this out. It's not super important to our specific problem. But anyway, all cones end up looking like this equation, where phi is equal to arctangent of that A value. So if we just head back up to find out what A is, if I look at the phi equals pi over 6 cone, A is, what is that? It's 1 over the square root of 3. Actually, don't really like explaining it that way. Let's start with 1 over A is equal to the square root of 3. I think that'll resonate a little better, right? I wrote my equation to be 1 over A times R. So 1 over A is the square root of 3, which means that A is 1 over root 3 or root 3 over 3, which is one of our tangent values off of the unit circle. Specifically, that one's pi over 6. And the other one, 1 over A in purple, that one's 1 over the square root of 3. So A is just the square root of 3. Again, that's a tangent value we know from the unit circle. And square root 3 is the tangent value at pi over 3. All right, so we've got our bounds for phi, which I think was the hard one on this problem. Now we just have to put the rest of it together. So I'll move that down to here. I need a triple integral. And the volume is equal to said triple integral. I'm triple integrating dv. Since all I want is the volume, all I have to integrate is dv. But don't forget, in spherical coordinates, you have to multiply in the Jacobian. Rho squared sine phi. You need that on every single triple integral. Might be worth looking at the formula sheet for spherical coordinates. I know we put the full transformations on there, like what x, y, and z are equal to. I don't remember if the Jacobian's on the formula sheet or not. Let's see. Oh, it is? Brilliant. Excellent. Look at the formula sheet. It tells you the Jacobian right there. So in case you forget it, there it is. So, don't say we aren't trying to help. So yeah, Jacobian's on the formula sheet. But we need the rest of this integral to come together. So I need a d rho, I need a d theta, and I need a d phi. So let's go write all of those down. Phi was from 0 to 5. You don't need color for that one. 0 to 5. Theta, we're going all the way around. There's nothing to stop us from doing the entire circle for theta, so we're 0 to 2 pi. Nothing told us to take like specifically the left half or specifically the right half or something like that. So 0 to 2 pi for theta, we just use our default choice. And we spent all that time figuring out our phi bounds. Just don't forget that pi over 6 is smaller than pi over 3. So pi over 6 goes on the bottom, pi over 3 goes on top for the limits on phi. And then we just have to integrate that thing. And I have a separable integrand. Rho squared, sine phi, and d theta, which means I don't need to do these in order. I can evaluate my 3 integrals independently of each other. So I'll have one integral that's sine phi d phi from pi over 6 to pi over 3. I can multiply that into another integral that is just d theta from 0 to 2 pi. And multiply that into a third integral that is just rho squared d rho. I don't know, how about red for this one? 0 to 5. And then each of those can be evaluated independently. And it looks like I need slightly more space. But the only way to get more space is to exit full screen mode. So thanks for the redesign, Microsoft. Just knocking it out of the park again. Okay, so if we evaluate each of these things, sine phi integrates to negative cosine. And then I just need to plug these two things in. So cosine of pi over 3 is 1/2. So this will be negative 1/2 minus a negative cosine of pi over 6. And cosine pi over 6 is root 3 over 2. We know we're calculating volume, so we should expect a positive answer out of this triple integral. I think that the phi integral is probably the easiest one to screw up of the lot, because it's got the most moving parts and the most exciting integral. So it has the most opportunities to go wrong. So it's worth just checking at this stage to make sure that your answer comes out positive, which in this case it does. Root 3 over 2 is bigger than 1 over 2 because root 3 is bigger than 1. So root 3 minus 1 is positive. So that part looks good. I think we got that part right. The rest of it, significantly easier. Integral of d theta from 0 to 2 pi is just 2 pi. And if I'm evaluating rho squared d rho, that integral from 0 to 5, that thing is going to be 5 cubed over 3 minus 0 cubed over 3. I won't write that part in. But then this thing can simplify if you want it to. Let's see. 5 cubed is 125 times pi over 3 multiplied by the rest of that stuff. The 2 and the over 2 simplify, so I can get rid of that part. Everything left over is just root 3 minus 1. So if you wanted to simplify, you can. That would be our simplified answer. If you wanted to just leave it in the blue, the green, and the red spot, where you've got each integral evaluated independently, since we were able to do that this time, that's totally fine too. Especially since you won't be working with a calculator on the proper exam. I think that sticking with simple numbers that then need to be cubed is a very valid place to stop. Because we won't look at evaluating the arithmetic anyway. So it's, again, not giving you calculators. So why would we care about the arithmetic? Yeah, it's not what we're here for. Okay. Picking up the pace ever so slightly to try and finish this thing in 50 minutes. A double integral over a general region. So I want to take the double integral of 6e to the 3x squared dx dy. And notably, e to the x squared dx, this integral has no simple antiderivative. Antiderivative would be like the fancy way of saying that that thing's not integrable. Not with the methods that we know, anyway. In particular, if I'm trying to find the indefinite integral, that's very complicated. I think that there are ways to do definite integrals on that thing. In particular, we've got e to the negative x squared. You integrate that over all real numbers. I believe your solution is pi. Let's back up because we don't need to go there. Point is, you try and attack this problem directly, you're going to get stuck. So I can't evaluate e to the x squared dx, which is the first thing that asks us to do, minus a couple of constants, but who cares about those? So if we can't integrate this thing directly, we need to change our order. So let's go do that. Breaking this thing down, I have dx first. So I have equations x equals 4 and x equals 4y. So I'm going to go graph those two things. And it looks like I've got space for a graph right here. I might move this and blow it up later, but for now, it's going here. So x equals 4 is a vertical line. X equals 4, that's this guy. X equals 4x. Some diagonal line, something like this. Or x equals 4y. Or this is y equals 1 over 4x. 1 over 4x, right? If I just solve it the other way. And then I've got y in between 0 and 1. So y equals 0, of course, just the x-axis. And I'd be willing to bet that this point right there is at a y value of 1. Quick inspection of our graphs will show that that's true. That's the point 4, 1. Right? That fits both of my two lines, x equals 4 and x equals 4y. So my region of integration, it's got to be that triangle. And what did we want to do here? We wanted to rewrite this integral in the other order. We're changing our order of integration and hoping that it becomes integrable if we do it that way. So let's give this thing a shot. I need to rewrite the thing with hopefully decent looking integral signs. If I'm changing my order of integration, my integrand itself does not change. It's still 6e to the 3x squared. It will only change if I do a change of variable, which aren't changing our variables, we're just changing the order of our variables. So our new order should be dy dx. Come through and maybe highlight that. I'm doing dy first now. Also going to move that down a bit so that I have space. So in the previous one, in the previous order, it was dx first, so we had to do left to right, which is why the blue line is on the left and the green line is on the right. That's the order when we're doing dx first. Left to right. I think that's correct in your orientation. Since we're switching to do dy first now, we have to go top to bottom, or bottom to top, depending on how you want to think about this thing. So I need a bottom equation, I need a top equation. And The bottom one. It's y equals 0. Y equals 0. That was this part right down there. And the top limit should be the blue line. So orange to blue, which means we're going from 0 to x over 4. Because that blue line is y equals x over 4. And then for x, it goes from 0 to 4. Mark that in green because that's our right limit for x. X is 0 to 4 after we fix the rest of that stuff. Now, this thing is a lot more integrable. So let's get to it. This thing, I'm doing the dy integral first. So that's going to be 6e to the 3x squared times. Well, the only y integral I have is dy. That's the only dependency I have in the integrand. So dy integrates to y, evaluated between 0 and x over 4. So x over 4 minus 0. Still a dx, still a 0 to 4 here. This thing has a particularly nice u substitution. If u is 3x squared, du is 6x dx. So that'll look like integral 0 to 4. How about we just pull that 1 over 4 out? 6x e to the 3x squared dx. And that will evaluate to just e to the 3x squared. Because again, very nice u substitution. So plug in our numbers. This will be e to the 3x squared, where x is 4. So let's see, 4 squared is 16. 16 times 3 is 48. I think that's e to the 48 minus e to the 0. E to the 0, of course, simplifies. I'll just call that 1. And there's an answer. Cool, yeah, the real fun part was making sure we changed that order. Continuing to move somewhat swiftly. Changing the order of integration on this guy. We're not even going to bother trying to evaluate the integral this time. Just make sure that we change the order around. So we've got dy first and then dx. So we'll do the same thing as last time. Sketch a graph. So I have two equations. This time they're for y. Apparently it's going to look like a heart. All right. Y equals 75 is my top equation. Does the bottom one also look like a heart? Nope, it's just a circle. Not sure what happened there, but hey, whatever. Y equals 3x squared. So I need to sketch those two lines over on the right. So y equals 75. That's just a horizontal line. Y equals 75. Oh, y equals 3x squared. That's a parabola. We're back to our usual y and x axes in two space. So we know what parabolas look like. Something like this. Yeah, good enough. So this is all together y, right down here, y equals 3x squared. I'll worry about changing over that equation to x in a moment. Now we'll come deal with the 0 to 5. The 0 to 5. for x. So if I look at those values, x equals 0 is the y-axis, and x equals 5, I'd be willing to bet it's where the parabola intersects that green line. So I'm only looking at the right half of the coordinate plane to find my region of integration. Going back to the green and blue parts, I know green is on top, blue is on bottom. So my region of integration must be this part right there. I'm going to come over here and gray out the left half of that parabola because it ended up not being necessary. I can see if I try to solve these equations for x, I'll get x equals the square root of y over 3. And I'll get x equals the negative square root of y over 3. But again, didn't need the left half of that parabolic shape, so it's out. That leaves us where? Finding our new limits. So starting with the x limits, that's going to be C and D on this chart over there. I switched from doing an up and a down limit, a top and a bottom limit, to a right and a left limit. So if I'm looking at my region and going left and right, my left limit is x equals 0, the purple line. The right limit is that blue parabolic curve. So the square root of y divided by 3. That's my right side limit. Then for the x limits, it's just between some numbers. Its lower bound is 0 and its upper bound is 75. And there's no integral to evaluate here, so we don't even need to try. It just said f of x. All right, let's hopefully keep pace with trying to finish this thing on time. I'm going to skip that one for now because it takes a while. I'll come back to it in the end when we've got time. I want to make sure that we also look at cylindrical coordinates because we haven't done that yet. All right. So, express the volume of the solid enclosed by the cone. Z equals root x squared plus y squared. And the sphere, x squared plus y squared plus z squared equals 8. With a triple integral in cylindrical coordinates. Ready, go. So, let's make sure that... Okay, so technically, the way the question is worded could be interpreted one of two ways, because there are two regions that kind of get enclosed by these two spaces. So let's evaluate it the nice way instead of the hard way. Again, I'm going to go to a projection into a ZR plane. Z here, R there. And I've got 2 bits. I've got a sphere, which projected into the ZR plane will look just like a circle. We know spherical coordinates now, so I'm just going to label this thing with a rho equals square root 8. That's the full shape. I'll worry about it being specifically in cylindrical coordinates in a minute. I've also got a cone. Right, this lad right there. This is the other super common cone, the one that we haven't looked at yet. Phi equals pi over 4. So that is going to be this guy. Phi equals pi over 4. We're getting a mix of both spherical and cylindrical coordinates here, just to make sure that we really know what's up. It also has the much nicer looking equation for polar coordinates, z equals r. And if we are looking for the volume that is enclosed by, we're looking for the volume that's enclosed by the cone and the sphere. Again, I think there are really two volumes that are enclosed by the cone and the sphere. Right? There's the part that is inside the cone and the part that's outside the cone, but both would be enclosed. It's a little bit of a roughly worded question. Well, happens sometimes. We'll be very specific about what we wanted in an exam question. So it might say something like bounded above by the sphere and below by the cone to make it extra clear that the region we're interested in is this region here. Right? If I tried to extend that into 3 space, we'd see that it looks like an ice cream cone. Right? It's got a cone and it's got a scoop of ice cream on it. That's our volume. Find the volume of the ice cream cone. And really that just means setting up our integral to evaluate the way that we want it to. And the part that we still need involves actually erasing all those lines to come and look at something specific. So my top part here, hey, come back here. My top part, again, it'll be that guy right there. Really, I should have only colored in the part on the right because we're only looking at the half plane. But well, I need this intersection point right there. A question I get rather frequently is why is r not the square root of 8? Because I look at that sphere equation, it clearly has a radius of root 8. Well, we're about to find out r, which is not rho, but r has an upper limit of 4. Take that back. R is an upper limit of 2 because 2 is the square root of 4. This little guy right here. It's going to be r equals 2. So what gives? Well, because we're evaluating this thing in cylindrical coordinates, I need to project the intersection of the cone and the sphere down into the xy plane. So we're going to go and do this again with y up here, x right there. Look over here. Da, 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 da. Stop it. Let me just okay, fine, whatever. This is going to be the equation r equals 2. That's the, again, intersecting the cone and the sphere. If we're looking at this thing from above, we'll see the green sphere on top of it. I don't know why I decided to just make it whatever. So the way we come up with that equation, again, I want the intersection of the sphere and the cone. The cone, I know, has an equation of z equals r. So z squared is just r squared. I get that from the cone itself. Right? That is my intersection part there. I know z is equal to r on the cone. So I'm plugging it into the equation of the sphere. From just regular old polar coordinates, I know x squared plus y squared is also equal to r squared. And that's equal to 8 because that was the sphere equation. So I've got 2r squared equals 8, which means r squared is 4 or r equals 2. So when I set my integral up, 1, 2, stop at 1, 1, 2, 3. We're just looking for volume, right? Yeah, volume of the solid. So we're just integrating dv. But if we integrate dv in cylindrical coordinates, we need to multiply by our Jacobian. So don't forget to multiply by r. Again, it's on the formula sheet. So r, every time you do an integral in cylindrical coordinates, fill out the rest of this thing. D, z, d, r, d theta, And what do we have? Z is first. Its lower bound was the cone, which is just R. Its upper bound is the sphere. Solving that for Z, I'll get the square root of 8 minus R squared. Mark that thing in green. So let's just do that. Stay consistent. R, then we spent a bunch of time solving for that one. It's between 0 and 2. Since that's the radius, the R radius at the intersection of the cone and the sphere. Remember that in cylindrical coordinates, our radius R gets measured to the z-axis and not the origin. So it's from the z-axis out, just perpendicular, straight out. And theta has been particularly boring today. It's always been our default choice in every example we looked at, 0 to 2 pi. And then I would evaluate that thing and go through and do it. In the interest of time, I just want to glance ahead at some of the stuff that I didn't get to. Here was another integration problem that I'll fill out in a second because I know I'm out of time. Changing some bounds and some stuff, getting something to look like cylindrical coordinates. I think this is an example where we finally won't see theta just between 0 and 2 pi. A couple of other cylindrical homework problems. Might not be a terrible idea to just glance at homework 9, which you should have already had completed, which is just our introduction to cylindrical and spherical coordinates. If you do go look at homework 9, just pay attention to the stuff that asks you to visualize shapes in these new coordinate systems. That could be helpful. Just getting a picture of what things look like in our other coordinate systems. And a couple of other reminders on integrating things nicely. Even and odd functions are super easy to integrate if we're looking between negative a and positive a. An odd function integrates to 0 because it has positive and negative area that's identical. So that adds up to 0. If I have an even function, that means that the right and the left sides are symmetric, they're reflections of each other, so I can just double 1/2 of the integral. I can just do 0 to a instead of negative a to a and double it. Examples of even functions. Polynomials with even powers, including constant functions. Cosine of x is an even function. Sine of x is an odd function, but sine squared is an even function. So yeah, bunch of examples there. Odd functions, odd powered polynomials, sine x, tangent x. Those are nice. That can be helpful for evaluating a few things. I did not yet look at a double integral in polar coordinates, but here is an example that I have done out ahead of time. Polar tends to look a lot like cylindrical, so I just kind of hopefully did some cylindrical problems that could help us get through those. There's a triple integral, just straight doing one, but I think those are pretty straightforward, so I left that one as an exercise. And then there's a few more examples on here, a bunch that are just kind of sketching out regions, because I think that that's helpful. So maybe look at some of those. But if you're pressed for time, I would keep just focusing on the problems that I did originally. You'll notice the ones I was particularly interested in getting through, I highlighted. And I almost made it through all of them. I was so close. But alas, there it is. All right, cool. So that's the end of class time. So I'll just stop it here. The last two problems that I didn't do, I will update later on, and I'll post a D2L announcement when I've got that work up. What'll be there? Okay, bye. Bye, 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 bye. Okay, and finishing up the last couple of problems that I didn't get to during class time. Here is the rest of that integral from, what is this one? Cylindrical coordinates. We had just gotten as far as sketching out the projection down into the XY planes when r went from 0 to 2. And then it was just a matter of evaluating that integral. I've included my work right here to just kind of keep track of where each of these pieces are going. Mostly the dz and d theta integrals are both pretty straightforward. Theta is just 0 to 2 pi, like we've seen several times. dz had a top and a bottom. It's really just that r integral that requires a little bit of extra work, since we need to integrate the square root of 8 minus r squared. Fortunately, there's an r being multiplied on the outside of it because of our Jacobian. So it is integrable with a quick Q substitution. Evaluating from 0 to 2 gives the result of 8 to the 3 halves minus 16. And then all that multiplied by 2 pi over 3. So just went ahead and did that one. Let's look at the last couple. So over here, we've got another triple integral problem. I'm just looking to set up. And what do we have? We keep looking at our top and our bottom functions and come over here and look at a z. And let's not like that one. Let's do magenta for z. This is z equals 25 minus x squared minus y squared. It's actually pretty hard to see all of that. So just move that up here. Move that up here. Z equals 25 minus x squared minus y squared. I'm not on the clock anymore, so I can work a little bit better on making my handwriting look okay. Z equals 25 minus x squared minus y squared for its lower bound. How about that one orange? I'm just picking colors out of a hat at this point. This guy is z equals 0. And with that, I can go make a sketch in the ZR plane with those two shapes. So my upper bound is the parabolic shape. Z equals 25 minus r squared. So something like that. Something that has a positive y-intercept. Bends down. Z equals 25 minus r squared. I should keep labeling my axes because we do like a few different ones here. So z and r. And our lower bound is just the plane z equals 0. That's this guy right here. So looking at their intersection or their projection down into the xy plane. Again, a rather convenient looking projection. It just gives us the circle r equals 5. R equals 0, r equals 5. Which we can also see if we go like at our y integrals. So over here, I'll have a couple of equations. Y equals the square root of 25 minus x squared, and also y equals 0. So if I sketch in, y equals 0 here, and y equals 25 minus x squared. I actually don't like the way all this color is coming together. There's too much of it. Let me change that r equals 5 circle to gray. And let me mark this one in. How about green? How about blue? It's gonna be y equals that guy. And then also we'll have y equals 0. We can do that in orange as well. I mean, we can't possibly have blue and yellow mixed together over here. that's that guy right there. Blue across the top. This is y equals the square root of 25 minus x squared, or lower bound then y equals negative square root 25 minus x squared. And by lower bound, I mean moving in the lower half of the circle. Our lower bound is y equals 0. X we saw went from negative 5 to 5. Also realized I haven't labeled these axes yet. These are just the x and the y axes. So our region of integration is this top half of the circle. So what does that mean for setting up our triple integral over here? Just put it so I still have both of those diagrams on screen. Our integrand this time is 8r. So we're not just integrating a volume. Because it's a cylindrical coordinate integral, don't forget to multiply by an extra r for that Jacobian. Throw in our dz, dr, and d theta, and then figure out our limits. So, z. It's up first. It's going to go from 0 to 25 minus r squared. R is next. Looks like it's going from 0 out to 5. As I can see from a couple of different perspectives that we have intersections where r equals 5. But then theta, we finally got one that was different. Our default assumption, again, is always 0 to 2 pi, but this time we're only evaluating the top half of that circle that's in the xy plane, or the first two quadrants, which means theta goes from 0 to pi, not 2 pi this time. And then this is a thing we can integrate. So let's get to it. This looks like 8r squared times the z integral, which is going to be 25 minus r squared minus 0. Still a dr and a d theta here. We mark theta in green because it's going from 0 to pi. And r still from 0 to 5. And try and evaluate this mess. This looks like just pi for the theta integral. Notice there's still no dependency on theta, so I can evaluate these two integrals separately or independently. Send the r integral. Let's see, the thing multiplies out to, what is 8 times 25? 200, I think. 200 r squared minus 8r to the fourth. So we can just come and evaluate those bits. This will be 200 over 3 times 5 to the third power minus 8 over 5 times 5 to the fifth power. Let me mark these guys off in blue just to kind of keep that marked throughout the problem. And I would just leave your answer right here. There's no cause for simplifying this further. Yeah, just leave that alone. All right, then the other couple that I wanted to talk about right now, I think I only missed this one. Rearranging a triple integral to have a different order for our bounds. So let's get to it. So I need to look at a graph out in 3 space. Actually, I need this guy to be a little bit longer. All right, so z is here, x here, and y there. So I want to sketch out a couple of shapes. One of those, the plane y equals 0. It'll just be the xy plane. And the other, we have a parabolic shape, paraboloid. Let's pick a color for that one. How about blue? Contrasts nicely with that magenta color. Yeah, pick that one off in blue. So it's a parabola. For y, it opens down in both of the other two directions. So something like that in the xy plane, and something like this in the xz plane. And then that means its intersection into the plane where y equals 0 looks like an ellipse. See if I can just scale this thing to look about right. It's kind of a little bit like that, and then adjust these other parabolic bits so that they intersect at the right spot. Shape hopefully like something a little bit like this. More detail. Even kind of like that. Almost like a football cut in half or something. So that's our 3D shape. We're looking to find an order if we were doing, looks like dy, then dz, and then dx. So if we're doing dy first, I need a projection into the xz plane. What this thing is going to look like. Fortunately, that one is pretty straightforward. It is just that elliptical shape right here. This might not be drawn to scale exactly because I need to find what some z and some x limits. So this is going to be x. That's going to be z. And I think I'll find for this ellipse that z is in between 2 and -2, while x is in between, let's see, what's 36 over 9? All right, 36 over 9 is 4. That's where I got z. 36 over 4 is 9. There it is. So x is in between -3 and 3. So again, to come up with those limits, basically set x or z equal to 0 to find the other one. To get z, set x equal to 0, and also y equal to 0. So I get 9z squared equals 36. So z squared is 4. Z is -2 to 2 for x. Again, with y and z both equal to 0, y is 0 because this is the xy plane. Notice the part highlighted in magenta. I'll get 4x squared equals 36. 4 over 36 is 9. Square root 9 is -3 and 3. So now I need limits for x and y and z. So let's go do that. Our y limits, pretty straightforward. They are y equals 0. Let's just not bother with the web work bit. Let's just write out a triple integral. dy, or fine, f dy dz dx. So y, we know it's going to go from 0 to 36 minus 4x squared minus 9y z squared. There we go. And then let's just make sure we were supposed to do z second. So z if we take that equation with y equal to 0 and solve it for z, so that's 0 equals 36 minus 4x squared minus 9z squared. We'll end up getting z squared was 36 minus 4x squared over 9. So z is plus or minus the square root of, let's call it this way, 1/3 the square root of 36 minus 4x squared. So slide that over just a little bit. Z is going to be negative 1/3 the square root 36 minus 4x squared to positive 1/3 the square root of 36 minus 4x squared. Somewhere I've got some space. Positive the square root 36 minus 4x squared. And then x, which is our last one, goes from -2 to 2. Look at changing this order 1 or 2 more times. This time we're going to do dz first. Taking the next integral down. Looking at that projection into the, doing dz first. So, well, I suppose I've kind of written this thing to look like a y and an x-axis, like that. A little bit different from our usual parameterization, but I think it's looking at the shape. I think that we can kind of see that I think there's a clear connection between these two. Because now I'm looking from top down at this parabolic shape with that elliptical edge right there. So that's our region now after we project it into the xy plane. This is going to be the equation y equals 36 minus 4x squared minus 0, since z is 0 in this case. And x, we already saw, is in between 3 and -3. Again, sort of looking at a rotated xy plane. Really, it should be like that if we're in our usual orientation. Right, with x going left and right, y going up and down. But I'm just looking at the 3D shape and coming up with the axis that way. So if I do that same thing, go look at another triple integral. It's also worth pointing out, this is at a y value of 36. So then I can see that if x and z are both 0. So again, integrating our function, this time we're doing dz first. And I don't actually remember what we did in the next order. dy, then dx. So if we're doing y second, 0 to 36 minus 4x squared goes here and there, with x going from -3 to 3. So it's the z bounds we got to get first. We need to come back to our 3D shape for that. If we're looking at an upper limit and a lower limit, we're basically just solving this same equation over here on the right for z, except this time we need the full y equals 36 minus 4x squared minus 9z squared. And solve that for z. It's going to be plus or minus 1/3 the square root of 36 minus 4x squared minus y. And then, how about orange? Those two are going to go here and there. Positive on top, negative on bottom for those plus or minus in our square root options. And lastly, we did the other two variables first before. Now we're gonna do x first. This time I'll put z on the vertical axis. And again, I'll put y on the horizontal axis like we did last time. And it's nearly the exact same shape. So parabolic in this direction with, again, the magenta edge right over here. That's y equals 0. Suppose I didn't label it last time. So I'll do that again here. And now this is the graph y equals 36 minus 0 minus 9z squared. Y comes out to 36. Z is in between -2 and 2. And if we go to get yet another triple integral, but with new limits, f dx first, then it looks like dz and then dy. Well, y finally gets the easy slot. It's from 0 to 36. The z limits, it's going to be negative 1/3 the square root of, I think we've heard this one before. This time it's 36 minus y, because now x is 0. Up to positive 1/3 the square root of 36 minus y. And for our x bounds, again, we're looking at y equals 36 minus 4x squared minus 9z squared. And much the same work that we'll see above, x is going to be plus or minus 1/2 the square root of 36 minus 9z squared minus y. Again, we'll look at just putting some orange dots around and say that these two limits go here. All right, and I think that will actually do it for this review. There are a bunch of extra problems down after all of these. If you want some more practice, you can look at those. I alluded to them at the end of class, so you've seen them earlier in this video. But again, that's it for me. Signing off. Okay, bye, 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 bye.